Hi, everyone. Welcome to our presentation of AutoSuggest. I'm So Yan from University of Washington, and this is a joint work with Ye He from Microsoft Research. Data preparation is a prerequisite for most business intelligence and machine learning projects today. It refers to the process of joining, reshaping, and transforming raw data into suitable format for downstream processing. It is estimated that users spend up to 80% of their time preparing data, and these users includes both experts like developers and non-expert users who use tools like Excel or Google Spreadsheet. In response, there's a recent trend to automate data preparation, which we often call self-service data preparation. And there's a generation of new tools for non-expert users like Trifecta and many more. To see data preparation in action, let's take this pivot operator as an example. It is a very common operation in BI and reporting. It takes as a flash relational table as input. In this case, a table with sales data indexed by year and region. And it creates a two-dimension pivot with region on the left and a year at the top. For data experts and the developers, they can write scripts using API like Pandas in Python to do the pivot. While developers can write code, non-expert users often struggle with this pivot operator because the interface to fully parameterize a pivot is rather complicated. In Excel, for example, to perform pivot, you have to use UI like this. It gives you all the attributes in the input table, and the user's task is to drag and drop these attributes into filter, legend, axis, and values. This is clearly not very intuitive. Actually, we find a large number of users question on places like Excel forums asking about how to do pivot. Okay, now we know pivot is a pretty complex operator and users struggle with it. But the question is whether we can do it differently. We believe that for non-expert users, instead of asking them to specify parameters, it would be more intuitive if we could simply present the top k likely pivot result so that they only need to pick the desired choices. This is because even though users don't understand the technical jargons, they typically know what they want to produce and are able to pick the desired result when they see the top k choices. So this is what we call intelligent suggestion or recommendation. In the broad context of data prep, there's a large number of challenging operators like pivot, unpivot, flatten JSON, etc. And beyond the single operators, sometimes users also want to ask questions like, what can I do next about my data? So what if we can intelligently auto-suggest the top k choices for all these operators? That, in a nutshell, is the premise of this work. In terms of intelligent suggestion, if we look at the state of the art, from both research literature and the commercial vendors, existing approaches cover a small number of operators. Furthermore, many existing suggestions use simple heuristics, which are often not very accurate in practice. So in this project, we built AutoSuggest. Here are the key highlights of the system. At a very high level, we built a systematic framework to learn from the experts, like developers and the data scientists, who really know how to deal with the data. How do we do that? Today, developers and the data scientists write a large number of scripts to deal with data in the form of notebooks and share with them in places like GitHub. Our idea is to collect and replace such notebooks so that we get to observe the decisions made by these experts on diverse input tables. We use them as training data to build predictive models that can suggest relevant data prep operations for non-expert users like Excel. We want to emphasize that through a systematic approach, this work can be easily extended to new operators that are not covered in the paper. We mentioned about Jupyter notebooks. Now I first give a brief overview of notebooks before showing how AutoSuggest works. For those who are not familiar with it, notebook is very popular and have become the de facto standard for practitioners in data science. There are 4.7 million notebooks as of May 2019, and the number is still growing fast. Here's an example of the notebook. It consists of pieces of data manipulation code interleaved with comments and visualizations. These notebooks are intended to be reproducible, so they are often accompanied by relevant data set. We find these notebooks to be really diverse in nature, covering a wide range of use cases, including data science, reproducible publications, data-driven journalism, so on and so forth. Here's how the system looks like. Given that there's a large number of notebooks available on GitHub, we first crawl and automatically replay the notebooks. The idea is that by replaying, we get to observe the exact input-output tables at each step. The collected data is used to build a variety of models, including machine learning based on optimization-based models. These training steps happen at offline. Then at online, AutoSuggest can take users' data and use these models to make relevant suggestions, such as the top case suggestions for the pivot, as you see earlier. Okay, now let's look at how we replay notebook first. In notebook replay, we focus on Pandas API, which can be considered the superset of SQL. This code snippet shows an example of Pandas code. Two tables, also known as data frames in Pandas, read from CSV, followed by two merge operations, which are essentially join. What is interesting about replaying versus simple static analysis is that we now get to see the exact input-output tables that data scientists get to see. And furthermore, from the code analysis, we know what are the parameters specified by the developer. This effectively becomes our training data and ground truths for predictive models. There are significant challenges in replaying notebook programmatically, as we are talking about millions of notebooks, and we need to automatically resolve issues like missing data files, package dependencies. I encourage you to check out our paper for more details. Okay, after describing how we replay and collect data, now let's look at how we build models. Let's look at Unpivot as an example, which is an inverse of pivot. In this example, we have a table as input showing the revenue for year 2006, 7, 8. Assume that we want to unpivot it back to a flat table where all the years are in the same column and the revenue are in another column. The predictive task is to determine which set of columns to unpivot or collapse. In this example, we can predict that the best choice to unpivot is these 3-year columns, because intuitively, these 3 columns are highly similar to each other, so they can be collapsed into one column. I want to mention that this predictive task of unpivot has not been studied before. We formulate the predictive problem using an optimization-based method. At a high level, we build a graph where each node corresponds to a column in the original table. Our first step is to use a regression model to predict column-to-column similarity, which becomes the weight of the edge. We then model the unpivot problem as a graph cut problem on the weighted graph to maximize the edge weight difference. Intuitively, we want to find a cluster of columns to unpivot, such that they are very similar to each other, but are also very different from columns outside the cluster. As another example, in the predictive task for join, we use a feature-based model, and we derive a rich variety of features that are indicative of likely join columns. Some of these features are intuitive, but not always obvious. For example, we find that people are more likely to join columns towards the left of the table than the ones on the right. The large data set we collect is a key reason for us to be able to leverage these rich features. So far, we have discussed how to predict for single operators. Now let's look at a different task, which is given available tables, the operator invoked in the past. We want to predict what is likely the next operator. Here's the model architecture. We leverage signals from 2 main parts. On the left, we have an RNN model that predicts the next operator based on the history. On the right, we run our single operator model as discussed before, which make predictions mainly on the input data. In the end, we combine these 2 components to make a final prediction. Okay, let's see evaluation. First, let's see how many data we have collected. For each operator, we replay a sample of up to 80,000 notebooks which contain that operator. The next row shows the number of notebooks that can successfully replayed. Even though our system tries to automatically resolve issues like missing data and dependencies, a significant fraction of notebooks will still fail to replay due to unresolved data and broken code. Next line shows the number of operators invocation successfully replayed. And the ones remain after we filter out uninformative invocations like repeated calls. Despite aggressive filtering, we are still left with 32.6 thousand cases for operators and 65 operator sequences. We show a subset of results in terms of prediction quality here. We split the invocation of these operators 80-20 as training and test. Each figure is for different operators. The y-axis shows the top 1 prediction precision, and the green bar is auto-suggest. We compare with a few commercial vendors, anonymized as vendor ABC, as well as a method adapted from research literature. We can see that auto-suggest significantly outperforms the other baselines. We also test the precision on the prediction for the next operator. Its precision at 1 is 72%, also significantly better than the other baselines. Okay, to conclude, we developed a novel auto-suggest system for self-service data preparation. We harvest a large amount of real data preparation tasks from replaying notebooks and use them to predict the single operators like join and pivot, as well as next likely operator. We find the proposed approach to be significantly more accurate than the existing methods. And we believe that this is a rich area for future research. Most of these operators have not been studied before and would be interesting topic for the future. And also, I want to mention that we plan to release the data in the near future. Okay, thank you for listening.